Welcome to Advanced Linear Algebra. Today, we are going to explore one of the most powerful and elegant concepts in mathematics, the orthonormal basis. If you have ever wondered how computers render 3D graphics or how quantum mechanics keeps track of probabilities, it all starts right here. Let us dive in. Before we look at the math, let us understand why this concept matters. Imagine giving directions. If you tell someone to walk northeast and then north, your directions overlap. It is confusing. But if you say walk east, then north, those directions are completely independent. In math, we call independent directions orthogonal. Now, if every step you take is exactly 1 standard meter long, your measuring stick is normalized. When you combine perfectly independent directions with a standard measuring length of exactly 1, you get an orthonormal basis. It is the ultimate, most perfectly organized grid system for any mathematical space. Now that we understand the idea, let us look at how it works mathematically. For a set of vectors to be an orthonormal basis, they must pass two tests. First is orthogonality. The inner product, which is like a generalized dot product between any two different vectors, ei and ej, must be exactly 0. This guarantees they are perfectly perpendicular. Second is normalization. The norm or physical length of every vector must be exactly 1. We find this by taking the square root of the inner product of the vector with itself. If the length increases or decreases, it distorts our standard unit of measurement, so it must stay exactly at 1. This formula we just saw leads us to an elegant shortcut. Mathematicians love efficiency, so they combine both the orthogonality and normalization rules into a single equation using the Kronecker delta, represented by the symbol delta ij. The rule is incredibly simple. If the labels I and j are the exact same, the delta equals 1, which proves the vector has a length of 1. If the labels I and j are different, the delta equals 0, proving the vectors do not overlap. So as you change the variables, the output perfectly flips between 1 and 0, capturing both of our strict conditions in one tiny package. Before we move on, let us see this with a concrete example. We are given two vectors, v1 and v2, and we need to verify if they form an orthonormal basis for the two-dimensional plane. First, we check for orthogonality. We calculate their inner product by multiplying their matching horizontal coordinates together, then multiplying their vertical coordinates together and adding the results. Multiplying the fractions gives us negative 1/2 for the first part and positive 1/2 for the second part. These perfectly cancel each other out, leaving exactly 0. This proves the two vectors are perfectly perpendicular and share no directional overlap. Now that we have proven they are orthogonal, we must check the second rule, normalization. We need to find the length of the first vector. We square each of its coordinates, add them together, and take the square root of the total, which is just the Pythagorean theorem. Squaring the fractions gives us 2 halves, which add up to 1. The square root of 1 is exactly 1. If we repeat this exact same process for the second vector, we will also get a length of 1. Because the vectors are perpendicular and both have a length of 1, they form a valid orthonormal basis. So we have proven that our vectors form a valid basis. This brings us to how we actually use them. In linear algebra, a basis acts as a core set of building blocks. You can create any target vector in the entire space by combining these blocks. The numbers that tell us exactly how much of each basis vector we need are called coefficients. In a normal, messy basis, finding these coefficients is a nightmare. It requires setting up complicated matrices and solving huge systems of simultaneous equations. But an orthonormal basis provides a massive shortcut that bypasses all of that hard work. This brings us to the magical shortcut formula. To find the exact amount of a basis vector EI needed to build our target vector V, we do not need to solve a massive system of equations. We simply take the inner product of the target vector V with that specific basis vector EI. The result is our coefficient, Ci. If the target vector aligns strongly with the basis vector, this coefficient increases. If it is perpendicular, the coefficient drops to 0. This massive shortcut is the primary reason why mathematicians and physicists are absolutely obsessed with orthonormal bases. Before we prove why this shortcut works, let us use it to solve a problem. We want to build a new target vector, W, which has coordinates 3, 4. We will use the orthonormal basis vectors v1 and v2 from our previous example. Our goal is to find the exact coefficients needed. To find the first coefficient, C1, we take the inner product of our target vector W and our first basis vector V1. We multiply their matching coordinates and add the results. Adding the fractions together tells us we need exactly 7 over root 2 units of the first basis vector. Continuing with our problem, we now find the second coefficient, C2. We take the inner product of the target vector W and the second basis vector V2. Again, we multiply the matching coordinates and add them together. This isolates the portion of W that points in the direction of V2. The math gives us exactly 1 over root 2. We now have both of our coefficients. By simply calculating two quick dot products, we found the exact recipe to construct our vector. This demonstrates the incredible time-saving power of working in an orthonormal system. Now that we have used this formula successfully, let us understand where it comes from. We are setting out to prove why the coefficient shortcut works. We start by writing our target vector V as a combination of our basis vectors, E1 through En, multiplied by their unknown coefficients. To isolate the first coefficient, we take the inner product of both the left side and the right side with just one basis vector, E1. Because the inner product follows the distributive property, we can spread it across all the terms on the right side, pulling the number coefficients outside the angle brackets. This is exactly like multiplying a number into a set of parentheses in basic algebra. Continuing our derivation, we now apply the strict rules of our orthonormal basis. Remember, the inner product of different vectors is 0, and the inner product of a vector with itself is 1. So every single term where the vectors are different instantly collapses to 0 and disappears. The only term that survives is the one where E1 pairs with itself, which turns into a perfect one. This completely destroys all the complicated math and leaves us with a beautiful, simple result. The coefficient C1 is simply the inner product of V and E1. The intuition here is that the inner product acts like a filter, perfectly extracting just the piece of the vector we want. Let us look at exactly what we just calculated. On this graph, you can see our standard x and y axes. Starting from the origin, we have our two basis vectors, v1 and v2, shown as solid arrows. Notice the right angle symbol between them? This visually confirms they are perfectly orthogonal. The dashed arrow represents our target vector W, reaching the point 3, 4. The dashed projection lines show how W is constructed. By traveling along the V1 direction and then turning 90 degrees to travel along the V2 direction, we arrive perfectly at our target. The diagram shows how the orthonormal basis creates a tilted but perfectly square grid system. Now that we have seen this visually, you might wonder why this matters outside of a math classroom. In the real world, computers constantly solve massive systems of equations for weather forecasting and 3D video game graphics. When computers use regular, non-orthogonal bases, tiny rounding errors multiply and snowball, eventually causing simulations to crash. An orthonormal basis prevents this because its perfect angles and unit lengths keep calculations completely independent and stable. Furthermore, in quantum mechanics, particle states are represented as an orthonormal basis, so probabilities always add up to exactly 1. Without this math, the digital signal processing that compresses audio and video on your phone would be impossible to compute in real time. To wrap up our lecture, let us review the most important ideas. An orthonormal basis is the perfect reference grid for any mathematical space. It requires vectors to be completely independent, meaning their inner product is 0, and normalized, meaning their length is exactly 1. By using this perfectly organized system, we can break down incredibly complex vectors into simple parts using the inner product shortcut, completely avoiding messy algebraic equations. You have now covered the full foundation of orthonormal bases, transforming difficult calculations into fast, stable, and elegant solutions.